Okay, this is the second lesson in chapter 25, section 1, second lesson of the week of April 20 through 24th. And what we're going to be talking about today is the alternating current, or AC, generator. Last time we talked about the fact that if I have a coil of wire and I run a magnet through that coil of wire, I will create an electric current. So if I take this wire and I take a magnet and I have those looped together, whether you can see it or not, when I move that magnet through there, I'm cutting perpendicular to those those wires, and as a result, current starts flowing. The direction matters. Let's say I do it this way. I can do my right-hand rule, figure out what the magnetic field is here. Current is going to flow one direction. When I pull that back out, the current will flow the other direction. And obviously it doesn't matter if I move it forward or back or move the magnet forward or back. It's the same basic principle. As long as the magnetic field is moving through a coil of wires, and as long as the coil of wires are linked together, electricity is going to flow. That is called an EMF. It was a misnomer. Misnomer meaning that we named it incorrectly. They did not know what voltage was. But for you, EMF would mean that it is a voltage that's produced by a generator. Now, there are two different types of currents in electricity. When we're working electricity, one is called AC and the other is DC. When I was a kid, we had a rock group in high school, AC/DC. They had a lightning bolt in between it. It was funny. A lot of people, because it was a hard rock band, thought that AC/DC stood for Antichrist, Devil's Child. But the fact that they put that lightning bolt in there probably meant that they were thinking of electricity. So I never really listened to them, so I don't have any opinion. But AC stands for alternating current, and DC stands for direct current. Now here's the difference. If I take a battery and I put we would normally draw this like this, but I'm going to do it that way, and we put a resistor here, and if this is negative and this is positive, the current will flow like this. We can almost think of it as water flowing downhill. But if I was to take the same thing and put a generator in there, what's going to happen is this generator, let's say when it's on this part, and the reason we do that sine curve, you'll understand in a minute, but you may remember that the voltage, EMF, was BLV sine of the angle. This looks like a sine wave. When this is going this direction here, let's say the current flows this direction, but when it goes here, that current's going to switch around and go backwards. Now, you may ask, doesn't it matter which direction the current is going? And the answer is sometimes, most of the time for things that we work with, no. It doesn't matter, just like it doesn't matter if a windmill is turning, whether the wind is blowing one direction or the other direction. That windmill is going to spin. It's very, very similar. So what happens with electricity is that if I can figure out a way of manually spinning a coil of wire inside of a magnetic field or a magnet inside of a coil of wire, I will produce electricity. And it's electricity that will switch from going one direction to the other. And that's why we call this the AC generator. I have something here. I showed you my little electric motor when we did it. This goes pretty fast, but I've got a battery. This is a direct current. And that spins, as you can see. As soon as I let it off, it's going to stop spinning. And you can just touch that down and it goes around. This is a little motor. The interesting thing about that motor, and I showed you this before, this motor is made up of a bunch of coils of wire, and inside of here there is a magnet. If I take, for instance, these paper clips, those paper clips will hang from there. So this coil sits inside of a magnetic field. Now think about it. When I turn this, I'm actually creating electricity. if I had a closed loop of wire. If I was to connect a light bulb to this, as I spin this, it should light up the light bulb. That was exactly what this guy was doing, this one that I showed you. When I spin this around, I'm taking a coil of wire, spinning a magnet. On this one, I'm spinning the coil of wire. Here I was spinning the magnet. This one I'm spinning the coil of wire. This right here is called a little alternating current generator. Once again, I have a light bulb. And if I turn this around, now this one, the way that it is set up, it generates enough that that light bulb almost looks like it stays on. I guess if I do this slow enough, you can sort of see it lighting up a little bit. But if I turn it long enough, that glows. All I am doing, I don't know if you can see well inside of here, this is the same thing as this. I am actually spinning this, and the outcome or the outflow, rather than putting electricity in and causing it to spin, I'm doing the exact opposite. And I can make that spin. Now, I want to show you something that's kind of interesting, because at this point you say, well, then you're getting something for free. No, you're not. This is where electricity is tied in with the rest of the laws of physics. In order to make that light up, I have to turn that. I have to do work here to make this turn. And it causes that to light up. I am transferring my own energy being used to turn this. I'm doing work on this handle, and as a result, I'm lighting up the light bulb. What a battery does is takes chemical energy and turns it into electrical energy. This takes mechanical energy and turns it into electricity. Now, let me show you something that's kind of interesting. I'm going to disconnect this. So at this point, if I spin this, it's not going to turn. But watch this. I'm going to turn this, and I'm just going to give it, I'm going to try and give it the same push. And that went around, I think, that went around 1.5 times. That goes around 2 times. In other words, there's a little resistance inside of here. But now watch what happens if I connect these together. By the way, when I spin this around, what I'm trying to show you, this demonstration, is when that spins, there is a little bit of friction trying to turn this motor, but I'm not creating any electricity. And so that'll spin around. Sometimes I can get it to go around maybe 3 times. Watch what happens if I connect this up and I do the same thing now. So what did it go around? Half at most. Oh, and you know what? I burned out my light bulb. That's okay. I don't need to show it again. But there's now resistance through there. And because of that, I'm trying to push electricity. I didn't really burn it out, but it won't light up anymore. I have more of those. In order to push that, it only goes halfway around. Why? Because it is now trying to push electrons through here. Some of you may have had, when I was a kid, we had a bike and I had a light on the front of my bike and it was connected up, and you would drive along, and when nighttime came, right up against the wheel, if this was the wheel of the bike, I had this thing and I would flip it over and it would rub against the tire and it would light up my light bulb. It took a lot more energy to ride that bike trying to light up that light bulb. It's amazing how much, if you have, let's say in a car, you have a 500 watt light bulb for your headlight. That means you have to be doing 500 joules every second. And if you remember back, lifting a 10 kilogram object, which is 20 pounds, lifting at 5 meters, which is 15 feet, is equivalent to 500 joules. But this is 500 joules every second. When I was in high school, my physics teacher had a bicycle that he had hooked up, and then he had it attached so that when he flipped a switch, it would light up a headlight from a car. And he would get the biggest guy in the class in there, and he'd be pedaling along, and he would flow that switch, and that would stop. Dead. You could not And then if you really tried, you might be able to get it to just barely turn and barely light up that light bulb. My point in telling you all of this is you're not getting something for nothing. But if we're smart, we can figure out something else that can turn the light bulb or turn the generator. And what things would that be? Well, we have hydroelectric. We put water in a dam and it falls down and it causes a generator to turn. If you go down below a dam that creates electricity, they have gigantic things underneath there called turbines, which spin around, and you've got this giant magnetic coil and you're spinning wires around inside of there. A wind will create electricity. Solar does it using chemical. That's a little bit different. But steam power, wind power, nuclear power simply boils steam. Most people don't know that, but a nuclear power plant does nothing more than simply boil water and uses that water to turn a turbine. And that turbine is a great big coil of wire which is spinning in a magnetic field and creating electricity. And of course, from our equation, the stronger the magnetic field, the more wire you have and the faster it goes, the more you're creating electricity. Now, what happens though is this. When you take a generator and you spin it around, think of having a coil of wire in here. And so I have a coil. This is a wire that's going into the board, coming back out, and we're connecting it up somehow. I have a video I'm going to have you watch because I cannot draw this on the board and show you how it works, but it's pretty easy once you see the video. But what happens is these wires are going to be spinning around in a circle. Okay? Well, what's going to happen then is this. If this is my magnetic field, this is north and south. If this is moving this direction, my finger's this way, the current is going into the board, and here the current is coming out of the board. And so what we're doing, and if you think about it, I've got a wire where I have that wire, and if it's coming out and it's going in here and out here, it's flowing in the same direction. We're going to call this point number 1. In fact, I'm going to take it and I'm just going to put this wire. Well, let's go ahead and do that. Then this is going this way, this is going this way, and the current is coming out, going in and coming back out. When we get to the top, this is moving this way. So this is position 1. This is position 2. This would be an X. We will have them both moving parallel. There would be no electromotive force. When this comes around and is this way, this is position 3. Now the wire that was coming out, the current is changing direction. And when we get to here, we're going the opposite way. There's actually 4 points as we go around. And if I was marking down what my voltage would be, I'm going to put this as Vmax and negative Vmax. And what's going to happen is we're going to start, you know what? I should have started up here. Let's start with this being position 1. Right here, we would have 0 current. When I move to here, let's call this maximum current. When I move to the 3rd position, I have back to 0 current. And when I go to the last position, this goes back to maximum. And then if it keeps going, I find that I have a sine curve. Voltage is going to go from maximum to minimum. The current will do exactly the same thing, because if I had a resistor across here, that voltage is going to be pushing the current. So current will go in exactly the same pattern. And we'll go like that. Okay? Now, there's an interesting thing that happens. I mentioned that I really don't care which direction the current is flowing for most applications. And so in a sense, I don't really care if this is a positive or a negative. So if I was to ask you, what's the average current? Well, the average current here, if you average this out, is obviously 0. I have as much above the line as below the line. If I added up all of these and subtracted all of these or added them, they'd come out to 0. But it turns out that if I think of this instead like this, the absolute value of it, what we call not the average current, but the effective current, is right at 45 degrees. And then the effective current is whatever the maximum current would be times the sine of 45. Well, the sine of 45 is square root of 2 over 2, and that would be 0.707 times the maximum current. And the same thing for effective voltage. The effective voltage is square root of 2 over 2 times the maximum voltage and 0.707 times the maximum voltage. Now, some of you might be panicking right now and saying, well, how in the world do I know what the maximum voltage is? Well, they would either give it to you or they would give you this information, and the maximum voltage is that right there. All right. And then the current is going to come. You're going to have to know what the resistance is. All right. What's interesting, though, is that power is always a positive number. Power is an absolute value all the time. So if you have the power and you want to know what is the average power output, the power of this average power is 1/2 the maximum power. That one is the same, what you would expect. It's half the maximum power. So there are some problems that deal with generators. There's a video that I want you to watch, a YouTube video, where it really explains, shows you that, and of course there's a discussion with that. So this will be problems in the book, problem 5 and 7. Those are odd, you'll have the answers for those. And then 60 through 72 even. And I'll give you the answers to those even problems. So, all right. We'll talk about some more applications on our next video, but that does that for now. So